Rigel blazes blue-white at Orion's edge, so bright it ranks among the most luminous points in the night sky, and yet its calm light hides a life that runs fast and deep. In this sleep-soft documentary, the story follows how a massive star is born from a cold cloud, how it changes fuel like layered hearths, and how its final fate can reshape a whole region of the galaxy. The tone stays slow, clear, and reassuring, while the science stays grounded in what is known and gently open where mysteries remain. If this kind of calm cosmic journey helps, please like the video, and subscribe for more long-form space stories made for rest. Now the sky grows quiet and Rigel's steady glow guides the mind into the long, peaceful cycle of starlight and matter. Rigel is a blue-white supergiant in Orion, shining at about magnitude 0.13 and standing among the brightest stars in the night sky. This matters because such massive stars live fast and reshape their surroundings, returning energy and newly made matter to the galaxy. By the end of this journey, the life cycle that carries a star like Rigel from quiet birth to a decisive ending feels clearer step by gentle step. In the familiar outline of Orion, Rigel rests like a cool blue beacon at the edge of the figure, steady enough to guide the eye, while its interior changes in ways too deep to see. The opening idea is simple and calming. The light that arrives tonight is not only brightness, but a record of balance, pressure, and time. A massive star is a place where gravity pulls inward with patient strength, and heat pushes outward with equal patience. And for a long while the two forces meet in the middle. The first clear payoff is that starlight is a kind of peace treaty renewed moment by moment. The star does not burn like a flame because there is nowhere to feed it. It shines because the core is so hot and dense that atomic nuclei can fuse. Fusion means small nuclei join into larger ones, releasing energy. That energy takes a long wandering path outward, bouncing and scattering through layers that behave like a thick, glowing ocean. By the time it reaches the surface, it becomes the blue-white light that makes Rigel look crisp and cold, even though its surface is still hotter than most stars. A second calm takeaway arrives early color as a clue. Blue-white indicates a high surface temperature, and high temperature hints at a powerful interior engine. Yet even this engine is not eternal. In a massive star, the great irony is that more fuel often means a shorter life. The reason is gentle and mechanical. A heavy star has stronger gravity, so it needs more internal pressure to hold itself up. It achieves that pressure by running fusion faster. Running faster means using fuel more quickly. The consequence is that a massive star can glow with astonishing intensity for only a small fraction of the time that smaller stars enjoy. In the quiet rhythm of the galaxy, Rigel belongs to the brief, bright generation. The story begins earlier than the light suggests, in a place without a single point of brightness at all. Long before a blue supergiant appears, there is a molecular cloud, a cold region where atoms and simple molecules drift with dust grains. It is dim and is heavy with potential. A molecular cloud is simply cold gas and dust gathered in space. The cloud is not calm everywhere. Turbulence makes it lumpy, and some lumps become dense enough that gravity starts to win. The collapse does not happen like a sudden drop. It happens like a slow tightening, as if the cloud is gently gathering itself into fewer, thicker folds. A visual anchor forms here. Think of thin mist on a winter field slowly becoming thicker in the low spots, not because anything rushes, but because the landscape quietly guides it. In space, gravity is that landscape. As gas falls inward, it heats up. Heat is motion, and compression forces motion to speed up. The growing object is called a protostar, not yet fully a star because its main source of energy is still the squeeze of gravity, rather than steady fusion. A protostar is a forming star heated mainly by gravitational collapse. Around it, a disk often develops a flattened swirl of material that feeds the center. The disk is not a decorative ring, it is a supply line. In the case of a future massive star, supply is the entire theme. To become something like Rigel, the forming object must gather an extraordinary amount of material before its own light and winds push the remaining gas away. Here the why this matters returns in a soothing way. The birth environment sets the entire life story like the first few notes of a long, slow melody, determining the key that everything else will follow. The next payoff is that mass is destiny, but it is destiny earned early. As the protostar grows, the core temperature climbs. There is a threshold that matters more than any dramatic moment. When the core reaches tens of millions of degrees, hydrogen nuclei can begin to fuse into helium. Hydrogen fusion is the process that powers most stars for most of their lives. In massive stars, this begins quickly and runs intensely. Once fusion begins in earnest, a new balance forms. Gravity still pulls inward, but the energy from fusion creates pressure that resists the squeeze. The star settles into a stable arrangement called hydrostatic equilibrium. Hydrostatic equilibrium means inward gravity balances outward pressure. This is not a fragile balance in the sense of constant danger. It is a stable balance, like a well-tuned instrument that holds its pitch because the forces are matched. Yet the balance is not static. It is a living adjustment where the core responds to tiny changes by expanding or contracting, warming or cooling, keeping fusion within a range that maintains support. A summary sentence slips in naturally. The star stays steady by constantly correcting itself. In a massive star, the interior is often convective, meaning hot material rises and cool material sinks, stirring the core like a slow dense pot. Convection is bulk motion that moves heat by rising and sinking. This stirring brings fresh hydrogen inward and carries fusion products outward, making the engine more efficient. Efficiency here is not a virtue that prolongs life. It is an efficiency that brightens the star and shortens the clock. The star pours energy into space at a prodigious rate. The surrounding region is shaped by this energy. Ultraviolet light can strip electrons from atoms in nearby gas, creating glowing regions. Stellar winds, streams of particles flowing from the star's surface, can sculpt cavities in the cloud that once fed it. A stellar wind is a stream of particles flowing away from a star. Even in calm narration, the implication is large. Rigel-like stars are not isolated lamps. They are active weather systems in space. At this point, the mind can return to the night sky and rest on the familiar pattern of Orion. Rigel's position makes it feel close, like a jewel on a nearby garment, yet it lies hundreds of light years away, and its light spends centuries crossing space. The distance adds a quiet perspective. The star is seen not as it is now in some absolute sense, but as it was when the light began its journey. The consequence is gentle, not alarming. The night becomes a museum of moments, each bright point a different time slice. Another clear summary sentence arrives: looking outward is also looking back. This is why Rigel is worth caring about. It is a bright, accessible example of a rare stellar class that lives quickly and ends decisively, and the processes that lead to that ending help explain why galaxies evolve, why clouds become enriched, and why remnants like neutron stars and black holes exist at all. The story does not rush toward catastrophe. It follows the slow logic of fuel pressure and layers. In the next section, the view drifts further back into the cold cloud, lingering on the conditions that decide whether a star becomes ordinary or immense, and why only a few regions can ever produce a light like Rigel's. The life of a massive star begins in darkness, and the summary is that cloud conditions decide how big the future star can become. A molecular cloud is a cold, dense region of gas and dust. In such a place, particles move slowly so heat does not easily push back against compression. This matters because a blue supergiant like Rigel requires an unusually generous supply of material from the very beginning. In the Milky Way, spiral arms gather gas into crowded lanes, where density rises by steady accumulation. Within those lanes, turbulence stirs the gas into knots and filaments, and some knots become just dense enough to start tightening. Turbulence means chaotic motion that makes dense pockets and empty gaps. A visual anchor appears here as a dark river of dust seen in silhouette against the starry background, hiding its cold weight in plain sight. The first payoff is simple star birth is not a spark but a slow change in balance. A region collapses when inward gravity outweighs outward pressure from heat and motion. The gene's mass is the rough mass needed for collapse at a given temperature and density. Gene's mass means the minimum mass that can collapse by gravity. The term sounds formal, yet the picture is familiar, like a blanket that sags when enough fabric gathers in one place. Colder gas has less pressure, so it sags more easily, and denser gas has more weight, so it sags more strongly. A short recap sentence settles in colder and denser pockets fall inward more readily. Cooling is the cloud's release valve because collapsing gas must shed heat to keep falling. Molecules and dust grains radiate energy away, letting the pocket stay cold instead of puffing back out. Opacity describes how well material blocks light and traps warmth. Opacity means how strongly matter blocks light. In thicker regions, dust shields molecules from starlight, so cooling continues. Even when gravity wins, it does not act alone, because many clouds are threaded by magnetic fields that guide charged particles. A magnetic field is an invisible pattern that steers moving charged particles. It can slow collapse by linking a small pocket to a wider volume, like threads that make cloth resist bunching. Yet the cloud is partly neutral, and collisions let neutrals drift past the field's grip, while turbulence tangles field lines into loops. The result is patchwork, not a single plunge of an entire cloud. Some regions hesitate and flatten, others thin out, and a few find a path inward. Another payoff arrives in a calm way. The cloud takes many tries and only a few succeed. Collapse is also influenced by outside pressures that arrive like distant weather. An expanding bubble from hot stars or a far supernova remnant can send a compressive wave across a cloud's edge. A shock wave is a fast pressure pulse moving through gas. The word can sound violent, yet over light years it often behaves like a broad push, raising density and letting gravity take over. A second recap sentence slips in a gentle squeeze can turn a quiet knot into a falling seed. Once contraction begins, the cloud often fragments, because the densest parts collapse faster than the rest. Fragmentation means one collapsing region splits into multiple smaller clumps. This is why stars are commonly born with neighbours sharing the same original reservoir. It is also why very massive stars are rare, because fragmentation divides the available mass into many smaller accounts. To build a Rigel-like star, at least one clump must keep access to a large inflow, and it must grow quickly. Gas streams along filaments toward the deepest gravitational dip, as if the cloud structure quietly funnels matter. Meanwhile, the growing clump warms and begins to glow from within its dusty cocoon, first in infrared and then more strongly across the spectrum. Radiation pressure is the push of light on matter. Radiation pressure means light transfers momentum when it is absorbed. With dust grains acting like tiny sails that push, can help clear the nearby supply, and stellar winds begin to add their own outward flow. A third recap sentence rests gently. A forming giant must eat before its own light pushes the table away. Here the reason to care widens without any sharp edge. The same feedback that limits one star's growth also shapes the surrounding cloud-carving cavities and compressing neighbouring regions that may later collapse. In that sense, massive star formation is both a personal story and a regional change in the landscape of gas. Rigel's present brilliance implies that its birthplace once stayed cold enough, dense enough, and coherent enough for one clump to dominate before the nursery dispersed. The mind can hold a final visual anchor, a dark filament slowly feeding an unseen centre, while faint warmth leaks out as soft infrared glow. Next, the story follows one winning clump as it becomes a hidden protostar and begins drawing material through a growing disk. A massive star's early growth is guided by a simple idea. Most of the real building happens while the star is still hidden. A protostar is a forming star heated mainly by gravitational collapse. This matters because a Rigel-like future depends on how efficiently matter keeps arriving before the surrounding cloud is blown apart. Inside, a collapsing clump rotation becomes important, even if the spin begins as a faint drift in the original cloud. As gas falls inward, it speeds up in rotation because angular momentum is conserved. Angular momentum means spin resists change unless torque acts. The result is a disk, a flattened structure that forms because infalling material cannot drop straight into the centre. The disk behaves like a quiet conveyor belt feeding the growing protostar through spiralling paths rather than direct rain. A visual anchor appears as a pale whirlpool of dust seen not in ordinary light but in the soft warmth of infrared, with the brightest point still buried at the centre. The first payoff is that disks are not accessories. They are the way nature solves the problem of getting material inward without piling up in a spinning ring. Inside the disk, friction and turbulence transport angular momentum outward, allowing some gas to drift inward. Accretion is the process of material falling onto a growing object. Accretion means growth by gathering in falling gas. In massive star formation, accretion rates can be high, and the protostar gains mass quickly, which changes everything about its internal structure. As the protostar swells, it is not yet a stable fusion engine, but it is already luminous, because infalling matter releases gravitational energy as heat. That luminosity begins to push back on the surrounding envelope. Another payoff settles in gently growth and self-limitation begin at the same time. Radiation from the protostar warms dust grains, and warmed dust re-radiates in infrared, which is why young massive stars are often discovered as bright infrared sources before they emerge in visible light. Yet the environment is crowded and dynamic, and the forming star is not alone. Neighbouring clumps may collapse into companion stars, and interactions can disturb disks, redirect flows and trigger bursts of accretion. A short recap sentence fits into the rhythm. The nursery is a community, and the community changes the supply lines. In some cases, a massive protostar forms in a region that is already dense with young stars, where gas is shaped by many overlapping winds and radiation fields. Here a gentle but critical idea appears. The forming star does not need perfect isolation. It needs continued access to inflowing gas, and it needs time to gather enough mass before feedback clears the area. Feedback means the star's light and winds altering its environment. Feedback means a star changes the gas that feeds it. The most intuitive form of feedback is the creation of an H2 region, a bubble of ionized hydrogen around a hot young star. Ionized means electrons are stripped away from atoms. Ionized gas is hot and expands, pushing against the surrounding cold cloud. The bubble behaves like a growing cavity, and for a forming giant this can be both a threat and a tool. It can choke off inflow, but it can also compress nearby gas into denser ridges that may continue feeding the disk through narrow channels. The image is soft, a warm lantern inside a fog bank hollowing out a pocket while leaving tendrils of denser mist that still flow inward along the edges. The second recap sentence arrives even as the star clears space. Some paths can keep delivering fuel. For the protostar, internal changes happen quickly. As mass increases, the central temperature rises and the object contracts toward a state where nuclear fusion can stabilize it. But contraction is not perfectly smooth. The protostar can bloat then shrink as energy transport shifts between convection and radiation. Radiative transport is energy moving by light within the star. Radiative transport means heat moves as photons diffuse outward. In the deepest regions, photons scatter so many times that their path becomes a slow random walk, and the time it takes energy to travel outward can be long compared with surface changes. This is why a young star can appear steady while its interior reorganizes. A third payoff appears. The interior is slow to reveal itself, so observers learn by indirect signs. Spectral lines, infrared glow, and the shapes of surrounding gas reveal how much material is flowing in and how much is being pushed away. In some forming massive stars, collimated outflows appear narrow jets that carry away angular momentum and carve cavities in the envelope. A jet is a narrow stream of fast-moving gas. Jets mean a focused outflow that clears channels. These outflows are not contradictions to accretion. They can enable accretion by removing the excess spin that would otherwise trap material in the disk. The sound of this idea is reassuring loss can support growth. As the protostar approaches the threshold for sustained hydrogen fusion, it becomes less like a swollen embryo and more like a self-regulating engine. The environment still matters, but the star's own structure begins to dominate its future. The stage is set for the first true ignition, not as a dramatic flare, but as a transition into a long-lived balance. Next, the story follows the moment when the core becomes hot enough for steady fusion and the star enters the main sequence, where speed and brightness define its brief brilliant youth. A massive star becomes truly steady when fusion begins to run as a reliable engine, and the early idea is that ignition is a quiet switch into balance, not a sudden flare. Nuclear fusion is the joining of light nuclei that releases energy. This matters because the moment a core can support the star against gravity sets the tempo for everything that follows, including how quickly a Rigel-like star spends its youth. The forming star has already been hot, bright and active while it grows, yet it is still powered mostly by the slow squeeze of gravity and by the heat of infalling gas. As the core contracts, temperature and density rise together, and a threshold is crossed where hydrogen nuclei can fuse efficiently. In massive stars, the dominant route is often the CNO cycle, a process that uses carbon, nitrogen and oxygen as catalysts. A catalyst is a helper that speeds a reaction without being consumed. The name can sound elaborate, but the picture remains simple. The star finds a faster gear for turning hydrogen into helium, and that faster gear produces far more energy per second. The first payoff arrives in a massive star ignition. Does not make the star brighter by a small amount, it gives the star an internal thermostat strong enough to hold a stable shape. Hydrostatic equilibrium is the balance between inward gravity and outward pressure. The star adjusts until that balance holds across its layers, so the surface stops changing rapidly and the interior settles into a long-running structure. A calm recap sentence fits into the rhythm. Stability is not stillness. It is constant fine-tuning. That fine-tuning happens because fusion is sensitive to temperature. If the core warms slightly, fusion speeds up, pressure rises, and the core expands a little, which cools it back down. If the core cools, fusion slows, pressure drops, gravity compresses the core, and temperature rises again. This is why a star can shine steadily for millions of years. Yet the steady phase in a massive star is swift compared with smaller suns. The reason returns to one physical fact: gravity is stronger, so the star must produce more pressure, and pressure comes from faster energy release. Luminosity is the rate at which a star releases energy as light. Luminosity means brightness measurable as energy per second. In a massive star, luminosity can be enormous, and the star pays for that brilliance by consuming its hydrogen more quickly. Another gentle payoff appears. The brightest stars are not the oldest, they are the most hurried. Inside the star, energy moves outward in different ways depending on depth. Convection can dominate where the gas is opaque and the temperature gradient is steep. Convection is heat carried by rising hot gas and sinking cool gas. A convective core in a massive star is like a slow churning heart mixing fresh hydrogen inward and bringing helium outward. That mixing keeps the fuel supply more uniform, allowing the core to burn efficiently. The visual anchor is warm and slow, a deep ocean current cycling through a basin, never rushing, always moving. Outside the core, a radiative zone may carry energy by photons that scatter outward. Photons are particles of light. Photons mean packets of energy that can be absorbed and re-emitted. The repeated scattering makes their outward journey long and wandering, so the star's surface responds to deep changes with a delay. This is why the outside can look calm even when the core's composition slowly shifts. A recap sentence settles the surface is the star's skin while the core keeps the real clock. As soon as the star enters the main sequence, its environment feels the full impact. Hot ultraviolet radiation streams outward, ionizing nearby hydrogen and carving an expanding bubble in the surrounding gas. Ionization means electrons are removed from atoms. Ionization means gas becomes electrically charged and hotter. The bubble expands like a slow breath, clearing cavities and piling gas into shells. Stellar winds also strengthen, carrying charged particles away at high speeds. A stellar wind is a flow of particles leaving a star. These winds matter because they carry mass away and they inject momentum into the surrounding region. The environment becomes a sculpted place with glowing edges and dark pillars where dense clumps resist erosion. In a region like Orion, such feedback helps explain why star formation happens in bursts and clusters rather than evenly. The why this matters returns in a calm, wide way. Massive stars are architects of their neighbourhoods, and neighbourhoods shape future generations. The star's own future is also shaped during this phase, because mass loss begins early. The more mass a star loses, the different its later evolution can become affecting whether it swells into a red supergiant, stays bluer, or transitions between states. A short payoff appears. The ending is not fixed by mass alone, but by mass over time. Rigel, seen today as a blue supergiant, carries the signature of this fast youth. Its blue-white colour hints at high surface temperature, and its brightness hints at a powerful engine that once burned even more intensely during core hydrogen fusion. Yet the main sequence phase does not last long, and the fuel in the core changes invisibly. Hydrogen becomes helium, and helium does not fuse easily at main sequence temperatures. Gradually, the core's composition shifts, and the core's ability to support itself with hydrogen fusion alone begins to weaken. Another recap sentence fits softly. The star's youth ends when its core runs out of the simplest fuel. This is not an abrupt shutdown, it is a slow transition. As hydrogen becomes scarce in the centre, fusion shifts into a shell around the core, and the core begins to contract again. The contraction raises temperature and prepares the next stage while the outer layers respond by swelling. In the next section, the story follows that subtle turning point when fuel depletion changes the star's structure, and the calm stability of the main sequence gives way to a larger, more complex supergiant life. A massive star leaves the main sequence when its core's simplest fuel is no longer available, and the early idea is that depletion changes structure more than it changes outward calm. Fuel depletion means the core runs low on burnable hydrogen. This matters because the shift sets the star on a path towards supergiant life where Rigel-like brilliance becomes both more dramatic and more complicated. During the main sequence, hydrogen fusion in the core provides the pressure that counters gravity. Over time, hydrogen is converted into helium, and helium ash accumulates in the centre. Helium is a nucleus of 2 protons and 2 neutrons. Helium means the product of hydrogen fusion that does not burn yet. Helium does not fuse at the same temperatures as hydrogen, so the core begins to lose its strongest source of support. Gravity responds in the most predictable way. The core contracts. Contraction raises temperature and density, like tightening a spring that stores more energy as it compresses. The first payoff arrives in stars running out of fuel can make the furnace hotter, not colder, because gravity keeps squeezing. As the core contracts, hydrogen fusion continues in a shell just outside the inert helium core. Shell burning is fusion in a layer around a core. Shell burning means the star burns fuel in a ring-like zone. This shell becomes a powerful source of energy, and its output pushes on the layers above it. The outer envelope responds by expanding. Expansion makes the surface cooler because the same amount of energy is spread over a larger area, and because the outer layers are less tightly packed. Surface temperature drops and the star's colour can shift toward the yellow or red even while the interior grows hotter. A calm recap sentence fits naturally. The core heats as the surface can cool. This is the moment where a star's appearance becomes an unreliable guide to its internal stage. The star can look cooler and larger, yet it is advancing toward more extreme interior conditions. The swelling envelope also changes how energy moves outward. Convection can take over in the expanded outer layers because cooler, more opaque gas favours bulk motion. The star's outer regions become like a slow, deep atmosphere with rising and falling currents that transport heat and mix material. The visual anchor is gentle, a vast, slowly boiling cloud layer, not violent but persistent, as if the star is breathing on a timescale of months and years rather than seconds. The second payoff follows expansion is not just growth, it is a rearrangement of the star's internal plumbing. For a massive star, this is the gateway into the supergiant phases. The name supergiant describes size and luminosity rather than a single temperature. A supergiant is a very large, luminous, evolved star. Supergiant means expanded layers and high brightness late in life. Some massive stars become red supergiants for a time with cool surfaces and enormous radii. Others remain hotter and appear as blue supergiants, or they swing between the two as the interior adjusts. These swings can happen because different layers respond differently to changes in burning and opacity. Opacity means how strongly matter blocks radiation. When opacity rises, energy can be trapped more easily and layers can inflate. When it drops, layers can settle inward again. In this way, a star can change its outer look without changing its identity as a massive object heading toward collapse. Another recap sentence slips in the colour is a surface mood, while mass and core state are the deeper truth. Rigel's blue-white light suggests that at least during the time it is observed, its surface remains very hot compared with red supergiants. That implies a compactness relative to the most bloated red phases, even though it is still enormous by everyday standards. Yet a blue supergiant is not young in the main sequence sense. It can be an evolved stage where the core has already changed profoundly. This is why Rigel matters as a teaching star. It looks crisp and bright, inviting a simple story, but it belongs to a complicated chapter where interior structure and mass loss can steer the outcome. Mass loss means the star sheds material through winds. Mass loss means the star slowly gives its outer layers to space. In supergiant phases, winds can become stronger and more structured, carrying away huge amounts of gas over time. This loss changes the star's weight and can expose deeper layers, altering later burning stages. It also enriches the nearby interstellar medium with material that has been processed inside the star. The why this matters returns in a calm, wide way. The elements needed for rocky planets and complex chemistry are partly delivered by stars that shed and explode. Even before any explosion, a supergiant can seed its environment. The outer layers can show signs of mixing, as convection and rotation bring fusion products upward. Rotation can stir a star's interior, blending layers that would otherwise stay separate. In a massive star, such mixing affects how long hydrogen lasts, how large the helium core becomes, and how quickly later stages arrive. The third payoff is that the life cycle is not a single-track schedule. It is a set of tendencies shaped by mass rotation and loss. Observationally, this stage can produce subtle variability. The expanded envelope may pulsate with the surface brightening and dimming as layers expand and contract slightly. Pulsation is a rhythmic expansion and contraction. Pulsation means the star's surface shifts in size and brightness. These changes are not signs of imminent disaster. They are the natural response of a complex structure finding balance. A final recap sentence settles a massive star, stays alive by adjusting, even as its fuel changes. In the next section, the story follows the star deeper into its supergiant identity, lingering on how a Rigel-like object can appear blue and steady, while building a layered interior that prepares the later, faster-burning stages. The supergiant phase is a new kind of steadiness, and the early idea is that a massive star can look serene while its core becomes a layered, changing engine. Blue supergiant is an evolved massive star with a hot surface and high luminosity. This matters because Rigel's blue-white appearance offers a calm window into a stage where the star's future is being prepared inside quietly and inexorably. After core hydrogen is exhausted, the star relies on shell burning around an inert helium core, and the core continues to contract. Contraction raises temperature until helium can begin to fuse. Helium fusion is the process of turning helium into heavier nuclei. Helium fusion means the core starts a new fuel after hydrogen. In massive stars, helium fusion proceeds mainly through the triple alpha process, where 3 helium nuclei combine to form carbon. The chemistry is complex in detail, yet the picture remains simple. The star turns a new corner, finding a fresh source of pressure to resist gravity. The first payoff arrives each new fuel stage is like opening a deeper, hotter room in the same house. The helium-burning core is surrounded by a hydrogen-burning shell, and above that lies the vast envelope that determines the star's observed size and colour. The star's surface can remain hot and blue if the envelope does not expand to the extreme sizes of a red supergiant, or if it contracts back after a red phase. Such behaviour can be influenced by mass loss rotation and changes in opacity. Opacity means how strongly matter blocks radiation. When opacity shifts, energy transport shifts, and the envelope may inflate or settle. A calm recap sentence rests naturally. The outer appearance is a negotiation between heat flow and gravity, not a single label. In a blue supergiant, radiation pressure plays a larger role than in smaller stars. Radiation pressure is the push exerted by light on matter. Radiation pressure means light can help hold layers up. With enormous luminosity, photons carry momentum, and when they scatter or are absorbed, they transfer that momentum to gas. This contributes to driving strong winds from the surface, especially when atoms and ions absorb light at specific wavelengths. A stellar wind is a flow of particles leaving a star. In supergiants, winds can remove significant mass over time, shaping the star's later fate and shaping the surrounding space with expanding shells of gas. The visual anchor is soft and spacious, a bright lantern wrapped in a faint outward streaming haze, where the haze is not smoke, but a river of atoms drifting into darkness. The second payoff follows. The star is already returning material to the galaxy long before any final explosion. This return material is not random. It can be enriched by the star's internal processing and mixing. Mixing means material from one layer is transported into another. Mixing means the star blends its interior zones. Convection rotation and wave-like motions can carry fusion products upward, subtly changing the surface composition and altering the opacity, which in turn alters the wind. In this way, the star's surface can carry hints of what is happening deeper down, even when the deepest core remains hidden. Another recap sentence fits the surface is a letter written by the interior but in a slow and partial script. Rigel, as a guiding example, sits in a region of the sky that makes it easy to find, and that accessibility is part of why it matters. It allows the mind to connect abstract stellar evolution to a specific point of light that returns season after season. The importance is not urgency, but clarity. Massive stars are the primary factories for many elements heavier than helium, and they shape the structure of star-forming regions through radiation and winds. Understanding one blue supergiant helps explain why galaxies have glowing nebulae, why some regions stop forming stars and why others are triggered to form new ones. The third payoff is that a single object can illustrate a whole ecosystem of cause and effect. Inside the star, the helium-burning core does not last as long as the hydrogen-burning core did. Helium provides less energy per unit mass than hydrogen fusion, and the star's luminosity remains enormous, so the core spends helium more quickly. The timescales shorten as the star moves forward. A recap sentence slips in gently each step after the main sequence is faster than the one before. As helium becomes depleted, the core contracts, again heating, until carbon can begin to fuse, and then later fuels can ignite in sequence. Those later stages are brief, and they build a layered interior that is often compared to an onion. The comparison is useful if kept soft. Each layer is a region where a different fuel dominates fusion with heavier elements nearer the center. Shell burning continues in multiple zones, each contributing energy and each altering the star's structure. The envelope responds to these changes with expansions, contractions, and sometimes mild pulsations. Pulsation is rhythmic expansion and contraction of the star's outer layers. It is a natural adjustment, not a sign of panic. The star is a complex instrument, always retuning itself as the internal source changes. The visual anchor returns as slow breathing, the surface shifts subtly over months and years, while the interior's deeper changes proceed on timescales that feel quick only compared with the main sequence. Meanwhile, winds keep flowing, carving cavities and shaping the star's surroundings into arcs and shells that can persist long after the star's visible phase ends. This is why massive star life cycles matter for the cycle of matter in a galaxy. They are not only endpoints, they are continuous contributors to the interstellar medium. In the next section, the story moves deeper into the star's layered burning, showing how successive shells form and why the approach to core collapse can remain quiet on the outside even as the core's options narrow. The interior of a massive star becomes a layered furnace, and each layer burns a different fuel for a shorter time. That single idea explains how a blue supergiant can look calm while its core races ahead toward a decisive ending. This matters because the layered structure sets the conditions for core collapse, and it also shapes what the star returns to space beforehand. After helium burning, the core holds a denser mix of carbon and oxygen, and gravity begins to tighten its grip again. As the core contracts, it heats up, and carbon fusion can start when the temperature climbs high enough. Carbon fusion is the joining of carbon nuclei into heavier elements. It releases energy but less efficiently than earlier fuels, so the star must run hotter to get the same support. A quiet payoff appears here later. Fuels do not last long because the star pays more for each unit of pressure. Carbon burning may occur in the core while other reactions ignite in shells like rings around a dim center. Shell burning means fusion in layers around an inert core. With time, the core grows heavier, while shells stack above it, each one powered by a different fuel, and each one affecting the layers above. The picture is often compared to an onion, but it can be imagined more gently like nested hearths in a deep stone tower. One hearth glows at the center, another warms a corridor around it, and higher corridors hold their own smaller fires. Every so often one fire fades, the tower settles inward a little, and a deeper fire takes its turn. A simple recap sentence fits naturally. The surface stays serene while the core keeps changing rooms. As burning advances, the star passes through brief stages that build heavier elements in sequence, and the timescales shorten sharply. Each stage requires higher temperature and higher density, and each one lasts far less time than helium burning did. A visual anchor can settle in the mind as thin layers of coloured glass forming in a kiln, each layer set by heat and time. Another payoff arrives: the star's later life is short because it is cooling as well as burning. At these extreme temperatures, the star loses energy not only as light but as neutrinos. A neutrino is a nearly massless particle that escapes a star easily. Neutrinos carry energy away with little delay, so the core can cool quickly even while it is hot. Cooling invites more contraction, contraction raises temperature, and the cycle accelerates. The result is that advanced burning proceeds with a strange urgency, while the envelope continues its slow supergiant rhythm. A recap sentence slides in deep inside the pace, quickens as the fuel options narrow. Convection and waves still stir the interior, and shells can interact in subtle ways. Convection means heat carried by rising hot gas and sinking cool gas. Stirring can mix fresh fuel into a shell, prolonging it, or move ash outward, changing how the next shell ignites. Burning can also occur in brief episodes where a shell brightens and then settles again. These episodes do not announce themselves clearly at the surface because the energy is absorbed and redistributed through vast layers. The star behaves like a thick blanket over a small heater, smoothing sharp pulses into slow warmth. Through all of this, winds continue to stream from the surface and carry outer material into the surrounding medium. That outward flow matters because it changes the final mass that will collapse, and it seeds nearby space with processed matter. Another recap sentence rests the star is both building layers and shedding layers at the same time. Eventually the core reaches a special point not because it runs out of heat, but because it runs out of useful reactions. Fusion releases energy only when it builds nuclei that are more tightly bound. Iron is a turning point because fusing iron does not release energy, it consumes it. Photodisintegration means energetic light breaks heavy nuclei into smaller pieces. This process absorbs energy and steals pressure from the core. Electron capture means electrons merge with protons to form neutrons. It reduces electron support and releases more neutrinos that escape. A quiet image can hold this. The core is like a support column whose material is being unmade as it bears more weight. Electron pressure is a resistance created by tightly packed electrons. It can delay collapse for a time, but it cannot replace the lost energy from fusion for long. A final payoff becomes clear: the star does not end from violence. It ends when the balance of support can no longer be maintained. In the next section, the view moves to the moment when the iron core gives way. Collapse begins fast and quiet at first, like a door finally opening inward. The iron core of a massive star fails in a way that is swift but strangely orderly. Collapse begins when support runs out. This matters because the same process explains supernova, light-heavy elements, and the birth of dense remnants. In the deep center of a Rigel-like star, fusion builds an iron-rich core that can no longer provide net energy. Ion fusion consumes energy instead of releasing it. The core is still extremely hot, yet it is now like a furnace that cannot add more heat to its own supports. Pressure falls behind gravity and the core starts to contract. One calm truth guides the scene: when the center shrinks, it heats, and when it heats, new losses appear. At these densities, electrons are squeezed into a crowded sea that resists compression. Electron pressure is support created by tightly packed electrons. For a time that pressure helps, but it has limits. As contraction continues, energetic light begins to break heavy nuclei apart. Photodisintegration means light breaks heavy nuclei into smaller ones. This breaking absorbs energy, like paying a cost to dismantle a structure. At the same time, electrons are captured by protons, turning them into neutrons. Electron capture means electrons and protons combine to make neutrons. That reduces electron support and releases neutrinos that escape almost freely. A neutrino is a tiny particle that rarely interacts with matter. Energy leaves the core in a nearly silent flood and the contraction accelerates. The outer star can remain visually steady while the center enters freefall. A visual anchor can be imagined as a quiet blue point in Orion. Far inside a similar star, the core changes in less than a heartbeat. As the core contracts, its density rises so fast that nuclei begin to touch and merge into a neutron-rich state. Neutronization is the shift toward matter made mostly of neutrons. In simple terms, the center becomes a single, compact object rather than a hot gas. This change happens not because the star chooses it, but because physics offers fewer options. Neutrons resist being packed too tightly, and the core suddenly becomes hard to compress further. Neutron degeneracy is pressure from tightly packed neutrons. In a calm picture, it is like reaching the solid floor beneath deep water. The inner core halts and rebounds slightly, and the outer core is still falling inward. The collision sends a shockwave outward, a pressure front racing through the infalling layers. A shockwave is a fast pressure pulse moving through gas. At first, that shock is not guaranteed to succeed. It loses energy by breaking nuclei and by sending more neutrinos away. The shock can stall, hanging in the star like a wave that rises and then pauses. The core releases an enormous burst of neutrinos, and some of that energy can help revive the stalled shock. Neutrino heating means neutrinos deposit energy in nearby matter. The heating is subtle in description but decisive in outcome. It puffs the material behind the shock, raises pressure, and helps the shock push outward again. Most of the energy leaves as neutrinos unseen, like a tide passing through everything. The visible flash comes later after the shock reaches the surface and the debris expands. Even in that force, the outcome is creative. The blast stirs nearby clouds and leaves enriched gas for future stars. Convection means hot rises and cool sinks. The shock gains strength and the star's outer layers begin to lift and break away. A clear consequence follows: the explosion flings newly made elements into space and drives a bright, transient sky signal. The light that is seen later is not the initial shock alone. It also comes from hot debris expanding and from radioactive nuclei decaying in the ejector. Radioactive decay means unstable nuclei transform and release energy. The expanding debris cools as it grows, like a glowing ember cloud thinning into darkness. Meanwhile, the remnant at the center settles into a new identity. If the core is light enough, it becomes a neutron star, dense and compact. If it is heavy enough, it can continue collapsing into a black hole. A black hole is a region where escape requires faster than light. These outcomes depend on the final core mass and on how much material falls back after the blast. Fallback means some ejected matter returns to the remnant. The same star can therefore leave different endings under slightly different conditions. A final visual anchor returns to Orion. Rigel's light appears as a cool blue point steady to the eye. Somewhere in the galaxy, a similar star ends in a brief flare. For weeks, it can outshine its host galaxy. In the next section, the focus moves outward from the collapse itself. It turns to the supernova and the extreme mass loss that follows. It follows how that energy travels through surrounding space and what traces it leaves behind. A supernova is not only an ending, but a moving wave of change that travels into the surrounding galaxy. The early idea is that the explosion's main work happens after the core collapses as energy and matter spread outward and reshape nearby space. This matters because Rigel-like stars influence future generations of stars even if their final moment lasts only seconds. When the revive shock breaks free, the star's outer layers are thrown outward at high speed. Ejector means the material expelled in an explosion. The ejector carries heat momentum and a chemical fingerprint of the star's interior. At first, it is extremely hot and bright, yet the brightness that reaches distant observers depends on how the expanding debris cools and how light escapes. Opacity means how strongly matter blocks radiation. In the early phase, the debris can be opaque, trapping light and letting it leak out slowly as the material expands. The image can be kept gentle, a glowing cloud that grows larger, while its glow softens like a lantern, seen through thick fog that gradually thins. The first payoff is clear. The visible supernova is a slow release of stored energy, not a single flash. As the debris expands, its temperature drops, but energy continues to appear from the decay of radioactive nuclei produced in the explosion. Radioactive decay means our unstable nuclei transform and release energy. One important example is nickel-56 decaying to cobalt-56, and then to iron-56 releasing gamma rays that heat the ejector. The energy is then reprocessed into optical light that can shine for weeks or months. The shape of the light curve, the way brightness rises and falls, helps reveal how much mass is ejected and how much radioactive material is present. The second payoff arrives a supernova, is also a measurement tool, a way to infer a star's hidden interior from a distant glow. In some cases, the debris runs into material that the star shed earlier through winds or outbursts. Circumstellar material is gas surrounding a star from prior mass loss. When the fast ejector collides with this slower material, shocks form and additional light is produced. The collision can create bright emission lines and extended brightness. A shock here is not an alarm, but a conversion of motion into heat and light. The interaction also shapes the later remnant forming rings, shells and knots that can persist for thousands of years. The visual anchor becomes a widening bubble, an expanding sphere whose edge brightens, where it compresses the interstellar medium. The third payoff follows. The explosion does not stop at the star's surface. It continues to work as it plows into space. The surrounding interstellar medium is not empty. It is a thin mixture of gas and dust, and the expanding blast wave sweeps it up. A blast wave is the outward moving pressure front from an explosion. As it sweeps up material, it slows down, converting kinetic energy into heat. The swept up gas can be heated to millions of degrees, glowing in X-rays. Meanwhile, cooler regions form filaments and arcs visible in optical and radio. Over time, turbulence develops behind the shock, mixing the ejected elements into the surrounding medium. Mixing means different materials blend through chaotic motion. This mixing is essential for galactic chemistry because it distributes heavy elements across regions that will later form new stars and planets. A calm recap sentence fits naturally. The galaxy becomes richer when debris is stirred into its gas. The elements released include oxygen, silicon, sulfur, calcium, and iron depending on the star's mass and the details of the explosion. Heavy elements are atoms heavier than helium. Heavy elements matter because they enable rocky worlds and complex molecules. Even before the final collapse, massive star winds carry carbon and nitrogen into space. The supernova adds a larger, deeper contribution, including iron group elements formed in the hottest zones. Yet the story stays measured. Not every explosion produces the same yields, and not every massive star ejects the same amount. Some collapse events may be faint with much of the outer material falling back. Fall back means some ejected material returns to the remnant. In those cases, fewer elements escape and a black hole can form more readily. This variability is one reason massive stars remain an ongoing puzzle. Another recap sentence settles the ending, is shaped by how much matter escapes. For a Rigel-like star, the most likely picture includes significant mass loss before the final collapse, plus a core collapse supernova that ejects large amounts of gas. Yet even in this likely path, uncertainty remains, and that uncertainty is part of the calm intrigue. It encourages careful observation rather than dramatic prediction. In the night sky, Rigel's steady brightness becomes a reminder that the massive star pathway is real and close enough to feel personal even though its timescales exceed a human lifetime. There is also a broader consequence. Supernova shocks can trigger star formation by compressing nearby clouds. Triggering means compression helps a cloud collapse. The same wave that disrupts and heats can also create new dense clumps at its edge, like a passing swell that gathers foam into lines. Over thousands of years, the shock slows and merges into the ambient turbulence of the galaxy. The remnant becomes a complex structure of hot gas magnetic fields and cosmic rays. Cosmic rays are high-energy particles accelerated by shocks. They can ionize gas and influence chemistry in clouds. Here, the why this matters returns softly. Massive star deaths are part of the galaxy's long circulation, moving energy and matter through many scales. In the next section, the focus turns from the explosion's outward effects to the chemistry it enables. It follows how heavy elements become part of dust and gas, and how that enriched material eventually returns to the quiet beginnings of new clouds. Heavy elements become the quiet inheritance of massive stars, and the early ideas that the bright life and explosive death of a Rigel-like star mainly matter because they change what future worlds can be made of. A heavy element is any atom heavier than helium. This matters because rocky planets' complex chemistry, and even the cooling of future clouds, depend on these atoms being present in the interstellar medium. In a young universe, hydrogen and helium dominate and gas cools less efficiently. Cooling is the ability of gas to radiate energy and lose heat. When heavier atoms appear, they provide many more ways to emit light, especially in infrared and visible wavelengths, and that helps clouds shed heat and collapse. The first payoff is gentle and practical. Heavy elements help the galaxy form new stars more easily. Massive stars contribute to this enrichment in two main ways, and both happen before any new star is born from the released material. First, winds and outflows shed processed gas during the supergiant phase. Second, a core collapse supernova ejects deeper layers and newly formed nuclei into space. The ejected material expands and cools, and some of it begins to condense into dust grains. Dust is solid particles made of elements like carbon, silicon, and oxygen. Dust matters because it absorbs light, shields molecules, and helps clouds cool. A visual anchor forms as tiny soot-like grains, drifting through a faint red glow, slowly collecting into darker lanes. Dust is also an ingredient in the chemistry of molecular clouds. On dust surfaces, atoms can meet and form molecules more readily than they can in open gas. Molecular hydrogen forms efficiently on dust-grained surfaces. Molecular hydrogen is H2, the main molecule in cold clouds. This matters because molecular hydrogen helps set the stage for the next generation of star formation. A calm recap sentence fits into the rhythm. The star's debris becomes a toolkit for future clouds. In the expanding ejecta, the distribution of elements is not uniform. Different layers of the original star are tossed out with different velocities and compositions, and turbulence mixes them over time. Mixing means different materials blend through chaotic motion. The mixing is incomplete at first, so the interstellar medium becomes patchy. Some regions are richer in oxygen, others in carbon or nitrogen, and the dust-to-gas ratio varies. Yet over thousands and millions of years, galactic rotation, turbulence, and repeated shockwaves blend the ingredients, smoothing extremes. The second payoff arrives. Enrichment is not a single gift, but a slow, repeated stirring. Some of the most important enrichment is not in the brightest visible phases, but in the quiet aftermath. When the supernova remnant expands into surrounding gas, it creates hot, thin plasma and cooler, denser shells. Plasma is gas in which atoms are ionized. Ionized gas emits characteristic light, and those emissions can cool the gas. In time, the remnant merges into the larger interstellar medium, leaving behind heated regions that slowly radiate away their energy. Cooling allows gas to settle back into denser states. The galaxy behaves like a breathing system, with cycles of heating and cooling driven by massive stars. Another recap sentence settles softly. The galaxy alternates between warmth and condensation. In this cycle, it matters that Rigel-like stars are short-lived but influential. They appear in clusters and associations, and their combined winds and supernovae create superbubbles, large cavities filled with hot gas. A superbubble is a large cavity formed by many stellar winds and supernovae. The cavity expands, sweeps gas into a surrounding shell, and that shell can become a site of new star formation. Compression is the act of squeezing gas into higher density. Compression matters because it can initiate collapse in regions that were previously stable. A gentle image can hold this as slow ripple on a pond, gathering floating leaves into a curved line. The ripple does not invent the leaves, but it organizes them. In space, the ripple is the pressure wave and the leaves are pockets of gas and dust. The third payoff follows. Massive stars do not merely add ingredients, they also arrange where ingredients collect. This arrangement affects where future stars form and how rich in metals they become. Metallicity is the fraction of matter in elements heavier than helium. Metallicity matters because it influences how stars evolve, how winds behave, and what remnants form. In low metallicity environments, winds can be weaker, so massive stars can retain more mass and possibly form heavier black holes. In higher metallicity environments, stronger winds can peel away mass and change the path toward collapse. This creates a quiet feedback loop across cosmic time. Enrichment changes the behavior of future massive stars, which changes how the next enrichment occurs. A recap sentence slips in the galaxy, learns from its own past by changing its chemistry. Rigel is part of a region where the interstellar medium is already enriched by countless previous generations. Its blue-white light shines through a sky that contains dark dust lanes and glowing nebulae, both of which depend on heavy elements and dust. Even the visibility of Orion's familiar pattern is shaped by this chemistry, because dust absorbs and scatters light, carving the sky into bright fields and dark rifts. The calm consequence is that the night sky's contrast is a trace of galactic recycling. The story now returns to a quieter phase where enriched gas begins to gather again into cold clouds. It moves from the outward spread of supernova debris back toward the inward drift of gravity. In the next section, the focus turns to remnants, the compact objects left behind, and how their gravity and radiation continue the life cycle even after the star's visible light is gone. A massive star does not vanish after the explosion, and the early idea is that the remnant continues the life cycle as a compact source of gravity and energy. A remnant is what remains after a star loses its outer layers. This matters because the remnant's behavior helps shape the surrounding gas, and it preserves the star's final outcome in a form that can last for billions of years. After core collapse, the center can settle into a neutron star, or continue into a black hole depending on how much mass remains in the collapsed core and how much material falls back. Fallback means some ejected matter returns to the center. In a calm picture, the explosion is like a wave that throws spray outward, yet some droplets arc back toward the source. If the returning material is substantial, it can tip a neutron star into further collapse. The first payoff is clear. The final ending is not decided by collapse alone, but by what the explosion manages to lift away. A neutron star is an object made mostly of neutrons, extremely dense and compact. Neutron degeneracy is pressure from tightly packed neutrons. That pressure can support the remnant against gravity up to a limit. Within that limit, the neutron star becomes a stable endpoint, and the star's former energy is stored in rotation heat and magnetic fields. Heat remains from the violent compression, and it leaks out slowly, partly as neutrinos early on and later as electromagnetic radiation. A recap sentence rests naturally. Even after the light of the original star is gone, the remnant can continue to shine in quieter ways. Many neutron stars are born spinning rapidly because the collapsing core conserves angular momentum. Angular momentum means spin resists change unless torque acts. As the core shrinks, its rotation speeds up like an ice skater pulling in their arms, yet here the motion is silent and extreme. If the neutron star also has a strong magnetic field, it can become a pulsar, a lighthouse-like source whose beams sweep through space. A pulsar is a rotating neutron star with beams of radiation. The beam is not a deliberate signal. It is a natural consequence of charged particles moving along magnetic field lines and emitting radiation. The visible effect when the beam crosses an observer's line of sight is a steady pulse. The imagery remains gentle, a distant rhythmic glow like a metronome kept by the galaxy. The second payoff is that compact remnants turn the star's final violence into long-term order, converting a brief collapse into a persistent measurable rhythm. Not all neutron stars present as pulsars, and not all are easy to detect because their beams may not sweep toward Earth or their emissions may be faint. Some are seen as X-ray sources warmed by their internal heat or by the accretion of gas from a companion. Accretion means growth by gathering in falling material. In some systems, a neutron star's gravity draws in gas that heats and glows, producing X-rays and occasional bursts. These details matter because they show that remnants remain active participants in their environments, even when the original star's surface and winds are long gone. Another recap sentence settles a remnant is not a tombstone but a new kind of engine. If the remnant becomes a black hole, the story becomes quieter in light but deeper in gravity. A black hole is a region where escape requires faster than light. The black hole itself does not emit light in the usual way, yet its presence can still be revealed when matter falls toward it and heats in an accretion flow. In isolated cases, a black hole can remain almost invisible, influencing only through its gravitational pull. In binary systems, it can announce itself through X-rays or through the motion of its companion. The calm importance is broad black holes created by massive stars are among the most common black holes in the universe, and they are key actors in later cosmic events, including mergers that generate gravitational waves. Gravitational waves are ripples in space-time produced by accelerating mass. The third payoff is that the end of one star can become part of a much later story far beyond the original explosion. Around both neutron stars and black holes, the expanding supernova debris continues to evolve. The supernova remnant is the shell of ejected material interacting with surrounding gas. As the shell expands, it sweeps up into stellar matter, slows down and develops filaments and knots shaped by turbulence and magnetic fields. Magnetic fields are invisible patterns that guide charged particles. They can thread the remnant like soft scaffolding, shaping the paths of energetic particles. Shocks in the remnant can accelerate cosmic rays, which are high-energy particles that move through the galaxy and ionize gas. Ionization means electrons are removed from atoms. This ionization affects chemistry in clouds, helping certain reactions proceed and influencing how clouds cool and collapse. A calm image can hold this an old wave on a shore long after the splash, still rearranging sand grains in slow motion. The remnant's energy gradually disperses into the larger interstellar medium, becoming part of the background turbulence that stirs gas across spiral arms. Meanwhile, the ejected heavy elements and dust continue mixing into nearby regions, ready to be gathered again by gravity. Their life cycle remains circular and patient. In a region like Orion, where bright stars illuminate nearby clouds, remnants from earlier generations may have helped shape the very conditions that later allow massive stars to form. The consequence is soothing cosmic events do not occur in isolation, but in overlapping layers of time where older echoes guide newer beginnings. Rigel's present light fits into this pattern as a visible waypoint, reminding the sky that massive stars are brief, yet their influence is long. In the next section, the view lingers on the stars, winds, and magnetic structures before the end, and on how those flows sculpt space in advance, preparing pathways that the remnant and debris will later follow. A massive star shapes its surroundings long before any final collapse, and the early idea is that winds and magnetic structure act like slow weather carving space in advance. A stellar wind is a flow of particles leaving a star. This matters because the wind carries mass away, changes the star's future, and builds a surrounding environment that the later supernova will expand into. In a blue supergiant like Rigel, the surface is hot and luminous, and photons push on atoms and ions in the outer layers. Radiation pressure means light transfers momentum to matter. The transfer is selective. Certain atoms absorb specific wavelengths, so the wind is driven by many tiny pushes, like a chorus of gentle taps that add up to a steady outward stream. The The first payoff is that light can do mechanical work, not only illuminate. The wind escapes the star's gravity and expands into surrounding space, forming a bubble of lower density gas. Over time, that bubble can grow to many light years across, bounded by a shell where the wind's pressure meets the interstellar medium. The shell is a slow boundary. It is neither a wall nor a sharp edge, but a region where gas is compressed and heated. A visual anchor appears as a faint transparent sphere around the star, with delicate ripples where it meets denser clouds. This boundary matters because it sets the stage for what happens later. When a supernova occurs, its shock will travel through whatever the star has already prepared. A second payoff arrives. The final explosion is shaped by the star's earlier breathing. The wind also changes the star itself by removing mass from its outer layers. Mass loss means the star sheds material into space. In massive stars, even modest changes in mass can change the core-to-envelope ratio influence, whether the star becomes a red supergiant and alter the final remnant. The effect is gradual, but the consequences can be large. Another calm recap sentence fits the star's future depends on the weight it keeps. Winds are not always smooth. They can be clumpy with denser knots and thinner gaps because the driving mechanism is sensitive to small changes in temperature and ionization. Clumping means the wind has dense pockets rather than a uniform flow. A clumpy wind changes how mass loss is measured and how the wind interacts with surrounding gas. As knots collide and merge, they can create small shocks that produce X-rays. These emissions offer a window into the wind structure, showing that the star's outward flow is a living pattern. The third payoff follows. Even a steady-looking star can have a complex atmosphere in motion. Magnetic fields add another layer of structure. A magnetic field is an invisible pattern that guides charged particles. In massive stars, magnetic fields may be weaker on average than in some compact remnants, yet even modest fields can channel the flow of ionized gas near the surface. Where field lines loop outward and return, they can trap wind material, temporarily forming magnetically confined regions. Magnetic confinement means gas follows field lines and can be held in place. When trapped material becomes dense enough, it can fall back toward the star along field lines, while other regions feed the outward wind. The image remains soft, a fountain, whose spray sometimes arcs back into its basin. This back and forth can produce variability, small changes in brightness, or spectral lines without any sense of urgency. Another recap sentence settles variability can be the signature of structure, not instability. Rotation ties these themes together. Rotation can flatten the star slightly, and can make winds stronger near the equator or poles depending on how temperature and gravity vary with latitude. The star's surface is not a rigid sphere. It is a glowing fluid shaped by forces. Over long times, rotation and mass loss can also influence internal mixing, carrying material between layers. Mixing means different layers exchange material. That exchange can change the surface composition and opacity, which feeds back into the wind. The system is circular and slow, like climate patterns that influence evaporation and clouds, which then influence the climate again. The why this matters returns with a wide calmness. Winds and fields are part of this galaxy's circulation, not sudden events. They feed the interstellar medium with gas and dust, they carve cavities, and they set pressure conditions in neighbouring clouds. In star-forming regions, these conditions can delay collapse in some areas, while encouraging it at compressed edges. Compression is the act of squeezing gas to higher density. The wind bubble's shell can become a site where gravity finds denser material to work with, yet the same wind can also erode and disperse fragile cores, limiting star formation nearby. The influence is mixed, and that complexity is part of the gentle intrigue of massive stars. A final visual anchor can settle on Orion again. Rigel's blue-white point seems still, yet it is surrounded by a faint expanding bubble of its own making, and the surrounding sky is full of dust and gas that respond to such bubbles over time. The story now turns from these shaping forces to the quiet rebuilding that follows. In the next section, enriched gas and dust begin to gather again, forming new cold clouds from the stirred and sculpted medium, and the cycle prepares a fresh beginning. Enriched gas returns to quiet coldness and new clouds form from the stirred leftovers of earlier stars. This matters because the life cycle only completes when debris becomes a birthplace again, not just a fading trace. After winds and supernovae spread atoms and dust into space, the galaxy does not keep them evenly mixed. Gravity rotation and turbulence gather material into lanes, and those lanes slowly condense into darker regions. A molecular cloud is a cold, dense region of gas and dust. Coldness is not emptiness. It is a state where atoms move slowly enough to stay together. Cooling allows that state to persist because energy can be radiated away rather than trapped. Dust grains help by absorbing light and re-emitting it in infrared, where the cloud can lose heat more efficiently. The first payoff is calm and practical heavy elements and dust make it easier for gas to settle into star-forming quiet. A visual anchor forms as a dark ribbon across a bright starfield, a place where starlight dims because dust has gathered. Within that ribbon, the cloud is structured. It is not a uniform fog. Turbulence makes it a network of filaments with knots at intersections where density rises. Filaments are thread-like concentrations of gas. In these threads, gravity begins to matter locally. A clump that becomes slightly denser pulls more material in and the density grows. Yet the process is not unstoppable. Internal motions can support a clump for long periods, and magnetic fields can slow collapse by linking a region to its surroundings. Magnetic fields are invisible patterns that guide charged particles. Even in mostly neutral gas, they influence collapse through weak coupling and through the way they shape turbulence. The cloud becomes a balance of competing tendencies, like a slow weather system that never fully rests. Another payoff appears star formation is regulated, not automatic, even when the ingredients are ready. Within the cold cloud, chemistry becomes richer than in the hot ejector. Molecules form freeze onto dust grains and return to the gas phase as conditions change. Molecular hydrogen dominates, but carbon monoxide becomes an important tracer because it emits readily at cold temperatures. A tracer is something easy to detect that indicates a harder-to-see substance. This matters because clouds are mostly invisible in ordinary light, yet their molecules carry signatures that can be measured. The cloud also contains pockets shielded from harsh radiation, where temperatures fall and density rises further. In those pockets, gravity gains an advantage. A recap sentence settles in the flow. Dense shielded regions are where the next generation begins. A visual anchor appears as a small darker core embedded inside a larger dark lane like a shadow within a shadow. In that core, dust blocks starlight so effectively that the interior cools to only a few tens of degrees above absolute zero. At such low temperatures, sound speeds are low and pressure is modest. Modest pressure means gravity can compress the gas without fighting a strong thermal pushback. When collapse begins, it begins gently with inward drift rather than sudden fall, and it accelerates as density rises. The collapse can fragment, making multiple protostars, or it can feed one dominant object if conditions and inflow allow. The environment decides whether a sun-like star forms or whether a massive star can emerge again. Here the why this matters returns with a wide lens. The galaxy's future brightness and chemistry depend on which kinds of stars form from these clouds. The material inside the cloud is not just gas. It carries the fingerprints of past generations, including dust and heavy elements from massive stars. That inheritance changes the cloud's behavior. Dust increases cooling and encourages fragmentation, which can favor forming many lower mass stars. Yet in dense pressured regions, massive stars can still form, especially where large-scale flows converge and keep feeding a growing core. Convergence is when multiple streams of gas meet and pile up. When convergence persists, a core can gather mass quickly even as feedback begins. The second payoff is subtle. The same enrichment that promotes small stars can still allow giants when the supply is large and sustained. Massive star formation is therefore both rare and repeatable, appearing in special places where conditions align. These places are often associated with spiral arms where density waves collect gas, and with the edges of expanding superbubbles where shells compress material. A superbubble is a large cavity formed by many stellar winds and supernovae. Its rim can become a ring of denser gas, a cradle along a boundary shaped by earlier stars. A visual anchor forms as a faint arc of gas glowing at its edge, with dark clumps tucked along the rim like seeds in a curved pod. Over time, those clumps may collapse into new stars. The galaxy appears to recycle its own sculpting. Meanwhile, the remnants of older explosions fade into the background turbulence, still contributing ionization and cosmic rays. Cosmic rays are high-energy particles that move through the galaxy. They can ionize gas in dark regions, which affects how magnetic fields couple to the cloud and how collapse proceeds. Ionization means electrons are removed from atoms. A small fraction of ionized particles is enough to let magnetic forces influence the motion of the larger neutral mass. This is why the leftovers of massive stars matter even in darkness. They tune the cloud's invisible physics. The third payoff arrives. What looks like silent dust is actually a responsive medium shaped by faint energy and slow forces. In this rebuilt cloud, the life cycle feels complete. The same matter that once glowed in a blue supergiant's light now drifts in cold filaments, waiting for gravity to gather it again. In time, one clump can become a protostar form, a disk ignite and shine. If enough mass collects, the resulting star can follow the same short brilliant path as Rigel-like objects, renewing the cycle of winds, enrichment and collapse. The scene stays calm because the timescales are long and the processes are steady. The night sky becomes a layered record of these cycles, with bright stars as brief highlights and dark clouds as patient reservoirs. In the next section, the view widens from a single cloud to the large-scale circulation of the galaxy, showing how countless such cycles overlap into one slow, coherent pattern. The wider galaxy turns individual star lives into a slow circulation of matter and energy. This matters because Rigel is not only one bright star in Orion, but also a signpost inside a larger system that keeps rebuilding itself. In a spiral galaxy like the Milky Way, gravity and rotation organize gas into broad lanes that curve around the center. These lanes are not solid arms, but patterns where gas lingers, becomes denser and cools more easily. One calm sentence holds the scale. The disk is a slow river, and stars are brief eddies within it. Within this rotating disk, the interstellar medium is never uniform. It is a mixture of hot, warm and cold phases that exchange material across time. Hot gas fills large cavities inflated by winds and supernovae, while warm gas drifts between cavities and cold gas gathers into filaments and molecular clouds. Pressure balance is the tendency for regions to adjust until their internal pressure matches their surroundings. Pressure balance means hot, thin gas can coexist with cold, dense gas when their pressures align. That coexistence matters because it allows a galaxy to store fuel in cold pockets while keeping energy in hot reservoirs. A visual anchor forms as a patchwork sky of dark lanes and faint glows with invisible boundaries where one phase fades into another. Superbubbles are among the clearest products of clustered massive stars. A superbubble is a large cavity inflated by many winds and supernovae. Its interior stays hot for a long time, and its rim sweeps up gas into a denser shell. The shell is not smooth, and it breaks into arcs and clumps where turbulence and magnetic fields create weak spots. Compression is the act of squeezing gas to higher density. Compression matters because it can help gravity begin collapsing clumps that were previously too diffuse to fall inward. A recap sentence fits without urgency. The same feedback that clears space can also gather new seeds at the edges. Rigel's existence points to such a landscape even without reconstructing its exact birthplace. A blue supergiant implies a region that forms many stars within a short time because massive stars rarely form alone. In those regions, feedback is shared. Feedback means stars alter the gas that formed them through light winds and later explosions. Ultraviolet light ionizes nearby hydrogen and creates bright nebulae, while dust lanes mark colder reservoirs that resist erosion. Ionized gas expands and pushes against colder gas-shaping pillars and ridges that look solid but are really flowing material. The scene stays gentle because the forces act over light years and over thousands of years like slow weather on a vast plain. On larger scales, the galaxy's rotation creates sheer a stretching effect because neighbouring orbits move at different speeds. Shear means nearby regions drift past each other over time. This matters because clouds must form stars before shear disperses them, and massive stars must form quickly if they are to appear at all. The timescales line up in a striking way. A giant star evolves quickly, and the dense structures that feed it are also temporary, so the whole process feels like a brief alignment of conditions. Another calm summary sentence holds steady, short-lived stars fit naturally inside short-lived clouds. Chemical enrichment spreads unevenly across the disk, then becomes more even through mixing. Mixing is the blending of gas and dust through turbulence and large-scale flows. Yet the galaxy never becomes perfectly blended, because new events constantly create new gradients. Some regions are slightly richer in heavy elements and others slightly poorer, depending on their recent history of star formation. Metallicity is the fraction of matter in elements heavier than helium. Metallicity matters because it influences cooling wind strength and the kinds of remnants that massive stars leave behind. Over long times, the disk's overall metallicity rises, and the galaxy becomes better at forming dust-shielding molecules and building complex chemistry. There is also a vertical circulation. Gas can be lifted above the disk by superbubbles and clustered explosions forming fountains that arc into the halo and fall back later. A galactic fountain is gas driven out of the disk that later returns. This circulation spreads heavy elements over wider areas and helps regulate the disk's pressure and temperature. It also helps explain why some clouds are found at surprising heights descending like slow rain back toward the plane. The image remains quiet, a faint mist rises, drifts, cools, and returns repeating without hurry. Against this backdrop, Rigel becomes a reassuring anchor for scale and meaning. It is one star, yet it represents a class that repeatedly resets the conditions of the interstellar medium. Its light suggests a short-lived high-impact life, but the galaxy absorbs that impact into long, steady circulation. The consequence is calming. Energy disperses matter, mixes, and new pockets of coldness appear again and again, ready to begin the cycle once more. The next and final section closes the loop back to Rigel's likely fate, and to the quiet continuity of matter through time. The cycle closes when one bright star is understood as a temporary arrangement of shared matter, and the early idea is that Rigel's true story is not only its eventual end, but its role in continual recycling. This matters because it turns a distant point of light into a calm explanation for why galaxies change, why clouds return, and why the ingredients of future worlds are never truly lost. Rigel appears as a blue-white supergiant, luminous and hot at the surface, yet governed by the same balance that shapes all stars. Gravity pulls inward, pressure pushes outward, and fusion supplies the pressure as long as useful fuel remains. Over time, the interior becomes layered. Fuels ignite in sequence, and the star moves toward a state where fusion can no longer support its core. The likely ending for a star of this class is core collapse, followed by a supernova that ejects outer layers and leaves behind a compact remnant. A remnant is the dense object left after the explosion. That remnant may be a neutron star or a black hole depending on final core mass and on how much material falls back. Fall back means some ejected matter returns to the center. The outcome is not a mystery designed to be sharp. It is a range of possibilities shaped by mass loss rotation and internal mixing. The first payoff is gentle and complete. The same physics that makes Rigel shine also explains how it will eventually stop shining in that form. The light seen in Orion is a present tense telling of those rules. It can be held as a steady anchor in a changing sky, and it can be treated as a quiet example rather than a prediction. The star's timescale is long compared with a human lifetime, and that distance in time encourages a calm way of thinking. The second payoff follows cosmic change is real, yet it unfolds with patience, and the night sky can be both stable to the eye and dynamic in truth. Even before any collapse, Rigel-like stars influence their surroundings through winds and radiation. A stellar wind is a flow of particles leaving a star. Radiation pressure means light transfers momentum to matter. These flows carve cavities, compress shells, and feed the interstellar medium with gas that carries new elements. Heavy elements are atoms heavier than helium. They matter because they increase cooling form dust and enable complex chemistry. Dust grains provide surfaces where molecules assemble more easily, and they help shield cold cores from harsh light. In this way, enrichment is not only a gift for future planets, but also a tool for future star formation. A visual anchor can settle here, a faint dust grain drifting through a dark lane, carrying within it atoms that were once part of a star's core, now moving slowly toward a new cloud. The third payoff becomes clear. The galaxy's most important work is often done by small particles moving through darkness. When a core collapse event occurs, the supernova shock spreads energy outward, heats gas and accelerates mixing. It also creates structures that persist for thousands of years, filaments and shells that gradually merge into the larger interstellar medium. Meanwhile, neutrinos carry most of the collapse energy away, leaving the remnant to cool and sometimes to pulse or to accrete. A pulsar is a rotating neutron star with beams of radiation. Accretion means growth by gathering in falling material. These remnants become long-lived nodes in the galactic network, influencing surrounding gas, and occasionally announcing themselves through X-rays or radio pulses. Yet the main theme remains steady matter, keeps moving through forms. It gathers into clouds, collapses into stars, becomes enriched and reshaped, disperses again and gathers again. A molecular cloud is a cold, dense region of gas and dust. It is the galaxy's reservoir, and it is rebuilt by the very stars it forms. The cycle is not a perfect repetition. Each turn adds complexity. Metallicity rises over time, dust becomes more abundant, and cooling pathways multiply. Metallicity means the fraction of matter in elements heavier than helium. Higher metallicity changes how massive stars lose mass, which changes what remnants they form, which changes the balance of enrichment and feedback in later generations. This is a quiet feedback loop, not an alarm. It is the galaxy learning its own chemistry, slowly adjusting what it can build from the same basic ingredients. Another calm summary sentence holds the loop the galaxy evolves by recycling, not by replacing. Rigel's place in Orion adds a human-scale comfort to this idea. The constellation is a pattern drawn by perspective, and Rigel is a point placed by gravity and time. Its light travels for centuries to reach Earth, and that travel turns space into a gentle archive. Looking at Rigel is looking at a chapter already written in starlight, and that chapter fits into a longer book that contains countless similar stories. Some chapters end with neutron stars, others with black holes, and all chapters scatter atoms that later rejoin clouds. The night sky therefore becomes a calm map of continuity. Even the darkest lanes are not empty, but full of future. The closing image is simple and slow. Orion rises. Rigel shines blue-white at the edge of the figure, and around it the galaxy continues its patient circulation, turning light into matter and matter, back into light, without hurry and without end. Rigel's blue-white point rests quietly in Orion, and the larger story settles into a steady rhythm. The galaxy keeps its slow circulation, gathering gas into clouds, shaping those clouds into stars and returning matter to space again. Nothing is rushed. Everything moves on timescales that soften sharp edges and smooth bright moments into long continuity. A massive star shines intensely for a short span, yet its influence spreads gently, carried by winds, drifting dust and expanding shells that fade into the background. The elements formed in deep interiors do not remain locked away. They travel outward, mix into colder regions, and become part of new filaments that darken the sky like calm rivers of shadow. In those filaments, gravity gathers what is ready to gather, and cooling lets the gathered gas stay together. Over time, small cores appear quiet and shielded, holding the same atoms in a new arrangement. The cycle is simple when viewed from far enough away. Light becomes change, change becomes structure, and structure becomes light again. Orion rises and sets, and Rigel returns with the seasons a stable marker for an ongoing process that never needs urgency to be real. The night sky holds bright points and dark lanes together, and the contrast remains gentle like a familiar landscape seen in low light. In that landscape, every ending becomes a beginning without strain. Matter moves from star to cloud, from cloud to star and onward, with the calm persistence of a tide that never hurries. The scene stays wide, quiet, and complete.